Idris, can you see my screen?
Yes.
Okay. So good morning to you all. I hope we are all doing well. In continuation to our reading, I'll be discussing the chapter 2, which is pre-trained models, pre-trained networks. Actually, I wanted to use slides, but then probably Mauritius has set a precedence to use the Markdown, and it's actually easier because we can see the codes and the text all in one. So the chapter covers actually the use of pre-trained networks. That is networks that has already been trained. So you just put in your own data. There is no need for training the model with your data set, with any data set. So the chapter covers running pre-trained image recognition models, introduction to GANs and cycle GANs, and then capturing models that produce text description of images, and then sharing models through Touch Hub. So I'll start with some. The text is a bit small. I wanted to use the VS Code, but it's not rendering my images properly. I don't know why. So I just use the notebook, the Jupyter notebook here. So we are going to learn how to use the work of best researchers in the field by downloading and running best interesting models that have already been trained on open large-scale data sets. This I already explained earlier on. We are going to use pre-trained models that have already been trained. All we have to do is put in our data to see the results. There is no need for training. And this is a very good way to start instead of you to try to understand every bit and cranny of how the planning works. You can just first of all observe how it works, then before following each step along the way, taking it step by step. But the first time, just observe how it works. So we can think of a pre-trained neural network similar to a program that takes input and generates outputs. That's it. You just give it the input and it produces output. You don't need to do anything. All the training and tuning and whatever has already been done for you. So using an off-the-shelf model can be a quick way to jumpstart a deep learning project, since it draws on the expertise from researchers who designed the model, as well as computation time that went into training the weeks. So, and of course, it will be faster because you don't have to waste any time training. So we are going to explore 3 popular pre-trained models. Actually 2, not 3, but yeah, 3. Let's say 3. Let's go by 3. According to textbook, a model that can label an image according to its content. Another that can fabricate a new image from a real image. So you give it one image of a horse, then it converts it, so it turns it into a, for example, zebra. That's the case of the book. And then a model that describes the content of an image using proper English sentences. And finally, we will learn how to load and run these pre-trained models in Pytorch. And we'll have an introduction on Pytorch Hub. So are we all together?
Yeah.
Okay.
Yeah. So let me just add something. As you said, so this chapter actually does not teach us deep learning from scratch. So it just like, as you said, just trying to let us see how deep learning works. So if somebody like feel like I don't understand how the deep learning works, yeah, that's fine. You are not expected to even know the details. So the architecture and everything is not taught here, but they are doing what is called pre-trained models. So as we discussed last week, what is all about deep learning? What we are doing is what learning is. Basically, what we are learning is just we are learning what is called parameters, right? So when you train your deep learning models, maybe one take 1 month, 2 months training deep learning model. At the end of the day, you will have trained models. So what is that trained model? So that trained model, what it contains is just some weights, some numbers that actually optimize or reduce the loss on the training. So now when somebody train his model, he finished everything, Now he has some optimized weight, and now people can release that models. When they release that models, now other people around the world, they don't need to train the models from scratch. Now they can use this, what you call pre-trained models. Now what they need to do is just to download the weights and now train and now do inference. So you don't need to train the model. So if we don't understand how the deep learning works from the beginning, this chapter, I think they even said it like, yeah, you just observe, as Ibrahim said, just look at how deep learning works. So that is just what I want to add.
Okay, Idris, want to add anything also? For anybody?
Yes, I don't know, maybe the book, or maybe the objective of this chapter did not state it, so maybe it's just an addition. So even the pre-trained models can be used to start your own training. So instead of starting to train from the scratch, so most of NLP nowadays just adopt a model and continue the training normally on a small data set that you have. So the accuracy usually is much more than.
Yeah. So also to just add something, as Idris said, so when you train a model, maybe on large data set, like for sentiment analysis, on English, the data set is trained on English. Now, this model, so this model you see has been trained on English, right? Big model, like billions of parameters. Now, when you can do this, they can train this model and now release the models as pre-trained. Now, you as somebody that working in Hausa, you can use this model because it learns some parameters. But what we do in NLP, we can do what is called fine-tuning. That is, we take some layers, last layers, and now fine-tune with Hausa text. So that is how we do in NLP. We take some pre-trained models that have been trained, and fine-tune with our small data on our language, then maybe it can use those pre-trained words, and it shows it has actually works. So yeah. Thank you.
Okay, in concluding remark to this, it actually works. That's what we use in our recent publication, the Niger Senti. We use a number of already pre-trained models, fine-tune them with our own data set, and then we get results. So yeah, any question? Or can we move on? Okay. So now we are starting with a pre-trained network that recognizes the subject of an image. Okay. As I go on, we may observe a number of codes within this text. I will not be running any of them. After the discussion, I will go to my notebook, VS Code, to see how it works. And Shamsu has also said that I'm reminded that we are not expected to understand the meaning of everything within the code. Some of the things will be covered in chapters ahead, but just now to get started and see how things work. So it's okay if we did not fully understand the codes or some of the, especially in the coding. So we'll get into that much later in the book. So we'll run a state-of-the-art neural network that was pre-trained on an object recognition task. We know what is object recognition task. For example, most of us are more familiar with NLP. You include, you want to classify a text, whether it's positive or negative. So object recognition is you provide an object, and then the computer recognizes what that object is. A picture, what is it? So a pre-trained network will explore here is trained on a subset of the Imagenet dataset. If you click, there's a link here. It will take us what is the Imagenet dataset. It's a very, very big dataset. Imagenet is a very large dataset of over 14 million images, 14 million pictures made by Stanford University. All the images are labeled with a hierarchy of nouns from the WordNet dataset, or rather database, the WordNet is like a lexical resource, like a dictionary. So all these images are labeled from the WordNet with a number of nouns from the WordNet resource. Imagenet originally from academic competitions. Most of data sets have their origin from academic competitions, very big competitions. Some of the competitions include Imagenet Large Scale Visual Recognition Challenge, ILS, whatever. Competition is based on a few tasks such as image classification, object localization, object detection, scene classification, and scene passing. Image classification, which we are concerned here with, that we'll focus on, is consists of taking input image and producing a list of 5 levels out of 1,000 total categories ranked by confidence. So what it does here is it takes an image, this problem, you give it an image, then it do some computation, some calculations, multiplication or whatever on that, and then it gives 5 levels for that image out of 1,000 possible outcomes, like dog, cat, whatever, up to 1,000. So to give you only 5, and these 5 are ranked by its confidence of what that is. For example, it will say dog, something percent, cat, something percent, like that. So it gives you it's ranked based on that confidence, describing the content of the image. So the training set for that consists of 1.2 million images labeled with one of the 1,000 nouns. For example, the dog refers to us, the class. So now we see how it works. You input the image of, say, a dog. Then some preprocessor happen, resizing, center, alignment. For example, in our own case, in center analysis, it will be removing of stop words, capitalization, whatever, on all of those. That is the preprocessing. Then you do a forward pass with the weights, because this model has already been trained, so there is no need for a back propagation. So you get your maximum scores, and then you have your labels ranked. I don't know if Idris want to add anything on this. Idris.
Yeah, I think it's clear. Okay. I think the reason for the resize, center, and normalize usually is to remove redundant space in the picture, so that the picture is not confused by other objects that might be in the background. So that's it.
Probably I'm assuming most of the time when we want to do machine learning, deep learning, and so on, we have to do pre-processing, meaning reducing the noise in the data and putting the data in a better way for the machine learning or deep learning to be able to make use of it. So we are going to end up with being able to take our own images and feed them into a pre-trained model, as I've explained. This will result in a list of predicted levels for that image, which we can then examine to see what the model thinks our image is. At the end, we will try to observe, okay, our model see the image we input is a banana. Is that true? No, obviously not, like that. The input image is first, okay, this is very important. The input image will first be preprocessed into an instance of a multidimensional array from the class Tensor. So it's an RGB image with height and weight. So images and blue. The coding of all images can be presented with this number combination. Their colors. So we'll have a tensor. Yes, the tensor we are going to have here will have 3 dimensions. That is the 3 colors for our RGB. And then the spatial information. The spatial is space. That means the width and the height. Will have these 3 dimensions of our RGB color and 2 spatial image dimensions of size, width, and height. So this image will be stored as a tensor containing of this parameter. Our model will take that preprocess input image and pass it through into the pretrained model to obtain scores for each class. The highest score corresponds to the most likely according to the weight. Yeah, the class with the highest number of weights is most likely what the image is according to model, if the model actually works. Each class is mapped one-on-one to a class level. The output is contained in touch Dataset with 1,000 elements, each representing the score associated with the class as explained. What Shamsu want? Anything to add? Shamsu?
Oh yeah, yes, yeah,
Maybe you
Doctor.
are muted.
Oh no,
Do
yeah.
you want anything to add here?
No, I mean, no. You explain it like this is the whole process of doing deep learning. I mean, the image. So what we should know is that the whole this image has 1,000 classes, right? So given, as you said, like we have an image, so we need to do some pre-processing and now do a forward pass because it's pre-trained model, and now we did a prediction. The reason why we have 1,000 here is we remember classification. So the image we have in the pre-trained basically has 1,000 classes. So that's why we have these scores, and now at the end they are ranked based on their stuff. So here we can select using maybe argmax or some stuff like that to take the best one. Yeah. So I think you already explained. Yeah.
And I think another thing to add here too, before maybe the number of classes might not cover the need of everyone. So to determine whether the pre-trained model will recognize what one needs, we may find the labels in the pre-trained image, so we can list the labels that we have.
Yeah. So I'll also add that
we'll see it in next chapter. So
it's like you flashed a bit.
oh yeah. So as I said, we said that each kind of data has different representation when you want to do deep learning. So for example, this image data, from the dog image to now we impute it into the neural network, though this is just a bag, we need to transform our image data into tensor. But the tensor representation of image will be of 3 dimensions, as Ibrahim said here. It will have the weight, height, and right, and the width, right? It will be 3 dimensional, unlike text we'll see. So one thing we should know, I think, in chapter 4, what it discusses is how can you represent different kind of data and pass it to your neural network. So to iterate, this chapter is basically just trying to show us how neural deep learning works. It's not like the deep. So if you don't understand anything, just be patient. In the subsequent chapter, they will take each step and explain it in detail how it works. Yeah, you can move on.
Well, Rabi, I saw your question. We'll come to it. I will try to address it the way I understand it, and maybe other members will also come in when we are trying to put. Okay, others with a network trained on Imagenet. So if known, this is a dataset containing 14 million images. To do so, we'll take a look at the Thought Vision project. This project contains a few of the best performing neural network architectures for computer vision, such as AlexNet, ResNet, and Inception version 3. We'll have I think we'll share to see this is our pre-trained and this touch vision. Later on, we'll see the the touch hub, where we can have a lot of we see project with a lot of pre-trained models. We can see how to search that and how to find these pre-trained models. I will not run this here. I'll run it later on in VS Code. So from touch vision, we're importing the models. Then you can use directory models. This will show us all the models. So when we have the models, I think I'll just go and do it now. so this, so it will just run. We are just importing. Then I already run this, but I'll run it again so that we see.
Me kake running ne ba ma ganin ai ko muna
I think doctor, you are sharing only PDF.
Oh, I'm sharing only that screen. So what I will do is I will stop sharing and I will share entire.
Yeah. So as Doctor is saying, he's talking about touch vision. So for any kind of task in Pytorch, they have their own stuff. Like for example, you can have touch text. So we have touch text. If you go, that is anything related to touch text, like our own case. So because I think those people that wrote this book, they are people interested in vision, that is image stuff. That is why they are giving example on vision. So yeah, we will go back to do our stuff related to text.
You know, you can see my screen.
Yes, we can see.
Yes.
Okay. So this is just an import statement importing the models from Touch Vision project. So you can just run it. Okay, all these codes are available. You can poke in the book, in the first chapter, towards the end of the first chapter, there is a link to the GitHub page of the book where all these codes are available for each chapter. You can just poke it to your GitHub page, and you can also easily download it to your computer so that you can run it locally on your computer. So this directory dir in bracket model will output all the models. So these are some of the models, the classes with capital letter. This one's the classes within the Touch Vision products, while the ones with small letter are just functions. So here, if you want to initialize this model, AlexNet, we just run this command. So this will initialize the model. Then this RESTnet will have a lot of different arguments, different parameters. For example, if we take RESTnet 101, it have 101 layers. And the pre-trained, we are initializing a pre-trained model. We just run it. So let's see. So this code gives a textual representation of some kind of information we saw in the previous figure, the one above, giving details, providing. Okay, when we run this code, we have this output. This is just text. This text is the same with the image we've seen. We have the input, then we have a number of layers: convolution layer 1, layer 2, layer 2, and then many bottleneck, and then the end. So what does it see? What we are seeing include modules, 1 per line. So this is a complete line. This is a complete line. So we have modules 1 per line. Note that they have nothing to do with Python modules. They are individual operations, the building blocks of the neural network. They are called layers in order the planning framework. So we have layers. If we scroll down, we'll see bottleneck modules repeating 101 of them. And this is from the 101, the RESTnet 101. If we choose a different RESTnet, maybe 50, we'll have 50 of them. Containing convolutions and other modules. That is the anatomy of a typical neural network for computer vision. A more less sequential cascade of filters and non-linear functions ending with layer. That is the FC. We don't have it on the diagram, but that is the last layer before the output. Producing scores for each of the 1,000 output classes. That is the out features. The RESTnet variable can be called like a function, can be seen like a function, taking as input 1 or more images and producing equal number of scores for each of that. So this is just like a function. We have functions are programming. When you call this function, then it will return, for our own case, we want it to return 1,000 scores for our input. Before we can do that, however, we have to pre-process the images. This we've already discussed the first time. When you input your image, you have to pre-process it. In order to do that, the television provide transform. Okay, we have this this function that will help us with our preprocessing. So this I've already run to see our the structure of our thing. So from Python, we are importing transform. So this transform is a function that help us with the preprocessing. For example, we can resize. We are resizing it to 256 by 256. Then we are cropping it to the center by this dimension 245. Anything out of that, it's going to be discarded. Then it will convert it to tensor. If we are doing the NLP task, we have to do what we call word embedding. So then we normalize the data so that data will be in the same range, in a fixed number of range. This is the mean we want, and this is standard deviation we want, so that we don't have negative values. Oh, my battery is dying. So somebody asked, Rabi, what is your question again? I think your question is here. Okay. The image may be altered.
Yeah, what I'm trying to say is that in the process of importing the image, okay, I know the size, or not the size, but the image may be altered. That is the what am I going to say?
The dimension.
In short, not the dimension. The image itself, it may be altered when you try to reduce the size of the image. So when you put that particular image, it may translate something else, not the particular image you wanted to input. So how is it going? How is someone going to overcome such kind of issue?
Idris, do you want to address this?
Yes. Usually, what you want to recognize in the image will be given. So you like, let's say, for example, in a Hausa visual genome data, you have the coordinates of the region within the image that you want that you are concerned with. So for the other regions, you don't care. So let's say you have the dog. Maybe in the dog picture, you might have house, you might have grasses, you might have, let's say, chair, but all of those are like noise because you don't want to recognize them. So the specific region you will be given usually. So to do the resizing, you resize it only to fit only that object, discarding other objects that will serve as noise in the background. So that's it. So if you want to recognize a different object within that image, you give a different coordinate so that it will go and recognize that. So I think what we mean here by 256, it means maybe it's a square. Yeah, 256 by 256. So you just resize only the picture to be 256 by 256. So to center, I think after doing that resize, when you do the center, it brings out the picture of the dog that you want to classify. So, but given the whole picture as it is, without doing the resizing, without doing the cropping, you may end up with the model confused as to what object you really want to classify.
Okay, I believe this test will be clear. We'll go ahead and remember that the whole, okay.
Yeah, one more thing to add is that you see, you may have different images, different size of image, right, in your data set. And so you may not train, for example, if we are using text in some ways, for example, sentiment class, we can trim all the length of the tweet or the length of into maybe 126 length or some stuff like that. So one way also, the best way to deal with different size of image is to downscale them to match dimension of more or less image available, right? So you can downscale that to one dimension so that they can learn from the same structure. What about if this one has this size, different kind of size, then there is some kind of some issue with the accuracy. Yeah. So this is one thing also regarding the image. Also, the image, when you downscale them, your model will train faster. Instead, for example, you have high resolution and stuff like that. So you may need to actually resize the image to, yeah. So this is basically transformation of image. Yeah.
Thank you for your response.
So I can see you drop a link to the repository for the description of these functions. So maybe if we look through that, then we may have an idea of what is the reasonable values to give.
Yeah, so
does that make sense?
Yeah, so
have you looked into that, and did you do they normally offer such kind of recommendation? For example, when you look at the function transform, then let's say you look at the transform dot resize, then do they give some values for that?
I think it's online now. Okay, he has come back. Doctor, your question, is it addressed to Dr. Ibrahim?
Just to all of have said information.
Whether it does, because even if it does, maybe I have not reached that. But
So
usually, maybe they are. Yeah, sometimes in specific tasks such as NLP, computer vision, and the rest, sometimes they are best practice. So maybe during the presentation, we might, if we know of these best practices, we might be like seeing them here, or maybe we might reach a point in the book where this kind of best practices have been stated. So yeah.
Yeah, so I understand where the bellow is coming. It's like bellow is coming from documentation purpose. Like, for example, in scikit-learn, you see, like, if all those conscious transformation, they will give you even default parameters, right? If you try to look up like the transformation, like you want to do in sklearn, right? So here in deep learning, as Idris said, like there is a lot of best practices that maybe you can provide the one you want to different one made, more or less. So you cannot actually, you may not see them. Maybe I don't know if they have such kind of default as we have in scikit-learn. But here you as a user also, you can provide the size you want to image. But I think the standard one that I've seen, like though I'm not image person, that's why I don't have the idea, is 256. I see they always resize 256. I'm not sure because I'm not vision person. So maybe one has an idea on how vision works, can talk much better. But yeah. So Ibrahim Naji, he has an issue with this internet, maybe, right?
I think he complained about his battery is running down.
Oh,
so maybe.
All right.
Because I heard him saying that.
My apologies.
Yes.
Right. I actually came back since when the Bello was asking the question, but because I was speaking, I assumed I was not mute. I was speaking, but nobody was hearing me. I just realized I was muted. Right.
So before Ibrahim continue, let me quickly share something so that at the middle. So here, one of the things we should know is that there is what we call Neuromatch Academy. Oh, sorry. Yeah. Sorry, I was talking. I don't know. I muted myself. So there is something called Neuromatch Academy, which is basically a summer school on deep learning. This is a course content, and I share a link in the Slack group that you can apply. I really recommend this summer school. You can apply it and get waived. The main idea we started doing this is the summer school will come maybe I think in July or something like that. If you get opportunity to be given a scholarship and you will get, is that they do Pytorch for deep learning. So they do, I really recommend it. But the idea is we want to get like the background of Pytorch. So for example, if you want to do machine learning, you need to get like at least Python, right? So here at this summer school, if you go, they are doing Pytorch. So with this kind of study session will give you a good understanding before you go to the summer school. And I really recommend, you can see the course outline. It's really deep learning. They will teach you from the beginning, from the very beginning. So our main idea now is this. After we finish this introduction of Pytorch, we learn the Pytorch. Maybe I can say we can learn the Python of deep learning. That is the language we use. We will come over here. We will start following this summer school Neuromatch Academy from the basic of deep learning, how to do deep learning, how to do more with parameters, advanced, so that we will get a bit of understanding. When you get into the summer school, you will learn more better. But also there's opportunity for those that are on top of deep learning already, that you can apply as a TA. So a TA actually, you will be a teaching assistant in the summer school, and you will get like a letter as they will give you a letter that you serve as a TA, and which is something great if you're applying for scholarship. So if we go through this Neuromatch Academy after our deep learning, then you will get a good understanding, and even you can apply as a TA because you finish this course. So when you apply as a TA, you can be as a TA, you will not be teaching anything, but you are facilitating the summer school. So that is one main aim that we started doing this book club. So let me allow Idris Ibrahim to continue the session. Yeah, we can discuss more after the session if you have any question. Thank you. Ibrahim, da ka iya ci gaba.
Okay. So I'm sharing my screen, my entire screen. Right? I'm sharing my screen, right? Nobody's answered. Yeah, okay. So here we just input our image. As I've explained, we've done the proposal. Okay, what I wanted to add here was, I think it's a very good question, and we can go and, even though a lot of attempts have been made to answer the question, we can still go and look through it more. Then we can discuss it maybe during our next class next week. So here we're just inputting the image. We input the library necessary to input the image, the base, then image, assign it to image, whatever, to open the image. And this is our image, and this is a dog. So we already have our function for pre-processing. So that is it. So we pre-process the image, and then finally we run our model. We import the touch, and then we import our own model. This is the image already pre-processed here. So here I have to what?
You've now run the previous image.
You have not run.
I skipped one. Yeah. So
I'm not sure if that's the one. Maybe you run this one. Yes.
I have to go all over from the beginning to start to run.
No, I think if you run that, it's okay, Dr. Ibrahim.
This one? Yeah, this one.
No, that image T.
Yeah.
Downwards.
This one. Yes.
Yeah,
Then
this one.
I think downwards.
Yes.
So now this one will work. So we now already run our model, and then we can evaluate it. What this will do is it will output a text of discourse, that all discourse that we have 1,000 of them. That is this one, and it put it inside. Now we have discourse 1,000 of them. Then we save it as text file. We open it and then save it as a text file, whatever. Then now we find the index of the maximum out of this. This we have 1,000 scores. Then we want to find the index. It's sort as an array with an index. So we find the index of the maximum output. Then we get its percentage. The one with the maximum output is the one most likely to be the image. So we have it, it says golden retriever, and this is the score, 96%. So it's 96% sure the email we inputted, that is this, is golden retriever. Is this golden retriever?
Yes.
Yeah.
I was surprised. What is golden retriever? I had to go.
Yeah,
and
it's
Google
a dog. It's the name of the
It's a
dog, I
dog,
think.
actually. Yeah, it's
It's
a
a
dog.
kind of dog.
I
Yeah.
had to go and Google that.
Yeah.
It's exactly the kind of image. So it's
Yeah.
96%. So it's correct. Actually, it was able to identify that the image we inputted was a dog, and the exact kind of the dog, golden retriever. So now we can just sort, this is just sort it out and find out the top 5 scores. So these are them. The first one, golden retriever, 96% sure, and it's correct. Then the next one is Labrador retriever. It's also a dog. These two still a dog, even though the confidence level is quite low, but they are all dogs. The last of the 5th one is not correct. It's not a dog, which is ball, but the top 4 are all dogs, meaning it was able to correctly identify that the image we inputted is a dog. It says it's a tennis ball, and this is maybe obvious, not obvious. It is likely to happen because mostly you throw tennis ball at a dog, and we have a lot of images with tennis ball and dog, so there is likelihood of it being classified as that. So we can see this. We can see how we use this pre-trained model to actually identify object, the image. I'll go back to my. Is there any question on this?
Doctor, can you go off?
Up where?
Yes. So starting from here.
Okay.
Aha. So, so here, in the, can you say exactly what you have? What is the purpose of this stage? The next stage where you import the image, right?
Okay. This image,
That
this
is
next
line
one,
14. Line
this is
14.
This one is for inputting the image.
This is the image you want to classify.
Yes.
Perfect. So, and then we go to the next step. Can you
This
go
is
down,
the image.
down, down?
Yeah.
Yes. So can you go down?
Okay. This one?
So, yes. So what did you do? What is the purpose of this stage?
This one is to this we are running our model, and this rest eval is to evaluate the model.
Yeah. So you know, we are not doing actually training, right? So if you are going to use pre-trained models, then you need to do what is called inference. So you don't train. So like you are transferring the weight, you know, that you download, and to make sure the, you know, just like training. So in the inference, like in, I think in Keras or TensorFlow, you do what is called compile on the, yeah. I mean, so here you eval is like you are for inference. That is all the weight, everything you now will now transfer to this object. So that is the meaning of this. So in maybe if you are training from scratch at this step, what we'll do is to put a function or something that will train the model. But since we are doing inference, everything is trained. We just use eval. Yeah. So you can see the parameters now that for the inference now has been now on this resonance object that we created. Yeah.
Yeah, yeah. So can you go down again?
I don't know. Anyone can also add an eval. Yeah, we have Idris or Tunde or said, can you add on this eval?
Yeah, I think most of deep learning, such as which I'm much more familiar with machine translation, what you do is you evaluate. So during evaluation, you are given some examples, and those examples you use your trained model to generate the target. So in here, what we are trying to generate is given a picture. We are trying to generate a list of names and their corresponding probabilities. So at the end, what we do, I think the rest of the code, what it does is it just select the 5 ranking probabilities and their associated labels. So, and that's it, yes.
Tunde, you want to add something on eval? Question? Oh, Idris, Ibrahim has issue, I think, still with his internet. So, yeah, today we have.
Yeah, generally it's a Nigerian problem. So maybe most of the time when we in Nigeria will be presenting, we might be having these issues. It's a network problem.
Oh yeah, yeah. So yeah. So what Ibrahim just said it did was basically try to use pre-trained models. As we said, this chapter is about pre-trained model, that you don't need to train your model from scratch. Already people have trained the models, for example, Google, Microsoft. Now you need to, when you want to train your models, you want to like use, basically what we are doing if we train model, we are trying to optimize to get best weight parameters. That's weight parameters, which are numbers, are the numbers that actually the model learns. Nothing more than that. When we train a model, what we learn basically are weights, some numbers. So when we release this as pre-trained models, so somebody may come, okay, I want to do machine translation or sentiment analysis. I can just go and take that pre-trained model that somebody has trained already. Now with the weight, just pick those weight and now come and now use it. That is pre-trained model. So what we did now, pre-trained model, it is, Ibrahim just download the pre-trained model and now say, okay, let me give a single image and see whether this pre-trained model will be able to classify it. Now that is what Ibrahim did. Like he downloaded a single image. He showed us the image, which is the image of dog. Now that image of dog, now he is trying to use the pre-trained model to classify the image. So we are not actually training a model today, but also, as I said, this chapter is basically trying to let us see how just amazing deep learning is. It's not trying to show us the null and bolt of deep learning. We'll see those in the couple of chapters, the next chapter. So feel free, if you don't understand this chapter, that's totally fine. You get understand the rest of the thing. Yeah. So you can even skip this chapter. It's not necessary. So yeah.
So one thing to add, maybe welcome back, Dr. Ibrahim. One thing to add is not all of the codes that you see here belongs to Pytorch. So some of the codes are just meant to do importing. Some of the codes are meant to do selecting from selecting the best probability or matching the probability with the associated image and the rest. So not all of the codes belongs to. So that means a person to do deep learning, you have to have some
Python
basic level knowledge on Python, because you need all these Python codes to do all other things apart from doing the actual training, or apart from doing the pre-processing, or apart from doing the actual evaluation and the rest. So you need other Python knowledge to do this importing and the rest.
Yeah. So one of the, as we discussed yesterday, one of the greatest prerequisite of this is you have understanding of Python. Because for example here, AlexNet so for example, all these stuff that you're seeing, they are basically
Dr. Ibrahim. Which page are you accessing? I think that's what I'm asking. Which page do you have this explanation?
This is from the book.
Inside the book?
Yeah, but I extracted this. This is a notebook I extracted from the book.
Oh, you extracted from the book and you add this text.
Yeah.
All right. Because when you run the model, this is what I expect. For example, each steps, then you mention what is there. So if you can go through this, that will help. Yeah.
Okay, we are running a bit out of time, so I think I will still skip this because we have 5 minutes. We can go overboard, but if we take too much time,
I think most of this has been explained in the notebook. So
actually, if I wanted to explain here, then I just go ahead to the notebook directly, because there I can run and explain. But what is here is basically, I already explained this. If we scroll down, we have what we see is bottleneck models repeating 101 times. And I also said that it can be 50, depending on which kind of ResNet we tick. This is ResNet 101. So I believe
so you can see also here. You can see also here we have pre-train equals to true, right? So what this means is that pre-train equals to true. It means we are downloading the pre-train weights.
Yeah.
So this is the argument, like he's downloading the pre-trained weight from ResNet 101. So this is the ResNet 101, the architecture, and he's downloading from the models. Yeah.
So what I want to see an image. What it generally does is it passes the image through a number of convolutional layers to do what the competition, multiplication, and whatever that we are going to see in chapters ahead. That text we have seen is just, this is the graphical representation. So now I'm going to skip all of this. This we will share maybe in our Slack group with the explanation, because we've all explained this, importing the image, running the model. Then we are going to start here, the GAN game. GAN means generative adversarial network. So I will start with an example. This example has been explained thoroughly in the book. I will summarize it. The expectation is we've all read the chapter. So if I explain wrong, somebody can correct me. It's just like a competition, not a competition. Let's assume somebody is a forger, a criminal that tried to forge fake images, fake pictures of, let's say, Picasso's, the old pictures that are very expensive, sold in the millions. So, but he's not an artist. He's not an artist. He's just a criminal. So no matter how much he tried to forge it, he will not be successful. If you take it to sell it to the experts, they will not buy it. They may call police on him, and they will tell him this is obviously a fake. Nobody will believe this is correct. Because why? He doesn't know what is doing wrong. Because you don't know what you're doing wrong if you don't know it at all. But then imagine a scenario where he gets an expert, a historian, a professor who is an expert in art, but crook, that they can work together. The con artist will try to imitate an image. He will take it to the what do you call it, to the professor who is a crook, who is have some immoral character. He will tell him, no, this is wrong. It's wrong because of that, and he will use that, go back, redo. He will continue doing that until it gets to a point where the immoral art historian cannot be able to tell if it's the real document or a forged document. So this is the scenario, and this is what happens in the GAN game. That's how the networks work. We have two networks, the generator and the discriminator. The generator tries to imitate images to look real, and then the other one, discriminator, tries to identify when it's been tricked, when the image is not the actual image. So this generator is trying to fool discriminator to provide to it an image which is fake, and this discriminator is trying to find out when it's been tricked. So that's the game, and this scenario generally explains how the GAN architecture works. So I will read it through. In the context of deep learning, we've just described what is known as GAN game, where two networks, one acting as a painter, the painter that paints the art, and the other as art historian, compete to outsmart one another in creating and detecting forgeries. GAN stands for Generative Adversarial Network, where generative means something's been created. In the case of our example, the fake image, the fake picture. Adversarial means two networks are competing to outsmart each other, and then we have the network, which is obvious. These networks are one of the most original outcomes of recent deep learning research. Remember, the main goal is to produce synthetic examples of a class of images that cannot be recognized as fake. So we want our model to be able to produce an image, a fake image that we cannot tell it's a fake. So generator takes the role of a painter in this scenario, tasked with producing realistic looking images, starting from an arbitrary input. Arbitrary input means just start with rubbish. So when it supplies rubbish to the discriminator will say this is rubbish because this is wrong, this is wrong, this is wrong. They continue doing that until it's one of them win. Then the discriminator network is immoral art inspector, a crooked art inspector needed to tell whether a given image was fabricated by the generator or belongs to a set of real images. Its goal is to find out what been tricked. These two networks design is typical for most deep learning architectures, but when used to implement GAN game, can lead to incredible results. So this is how it works, the graphical representation. This is the, what do you call it? What is it? Generator network. Yeah, generator network. It do whatever it produce something. Maybe trying to produce a man. So the discriminator will be able to tell us whether it's real or fake. So they continue doing that until it's able to fool it. For example, here it draws it and it looks like a man, and it says it's look good. I don't know if somebody wants to add anything here based on our own reading on this GAN game. Idris. Amina.
Yes. The game usually start with the rubbish, which is this ... as Dr. Ibrahim explained. The main target of this is enabling the generator to win. So if the generator is able to win, it means that your network is intelligent enough to produce fake images that can disguise as real images. So that's the end goal of this GAN game, when the generator wins. But when the discriminator wins, it usually when the picture is given, it tries to point out that, yeah, this is fake, but why does it make it fake? So the generator will use that information to try to better the quality of its own generation. So usually this is applicable not only in computer vision, but also in text processing, such as machine translation. So it's called reinforcement learning in some ways. Yeah. So one is trying to reinforce the other. Yeah.
Oh, very good. Thank you. Anybody want to add anything? Is Tunde here? I don't know. Yesterday he was a bit vocal. Okay, we can move on. Then we have an improvement of the cycle of the GAN, which is the cycle GAN. An interesting evolution of this computer is this concept is the cycle GAN. The cycle GAN can turn images in one domain into images in another domain. It can turn a zebra into a horse or a horse into a zebra without the need to explicitly provide matching pairs in the training set. Meaning, we don't need to give it. The data doesn't have to be in pairs. You have one pair of image of horse and say, for example, zebra. It doesn't have to be in pairs. All it needs is a set of images for horse and a set of images for the other class like zebra. We have a cycle GAN workflow of tags in the photo, in this photo, and vice versa. Note that I will explain it when I come to the image. So we have generator A learns to produce target distribution, that is zebra, from a different distribution from horses, so that the discriminator can't tell if the image produced by the horse photo is actually genuine or fake. So you keep trying. For example, we have a picture of the horse. You keep trying to draw a zebra from that. Then the discriminator will continue to tell you, this is not a zebra, this is not a zebra. It will continue editing, but it change that image to a zebra. So we can have two images. We can have from one image, we can convert that image to image of a different. I don't know if this is clear. At the same time, the resulting fixed zebra is what I will explain this. So what happens here is we have an input. For example, this is an input of a horse. Let's take it as that, as a horse without the lines. So it tried to convert this image into a zebra. Then the discriminator keep telling it's fake, it's not a zebra. Then it continue optimizing until it gets it correct. But what happens is when it tells it this is not a horse, then it passes through another discriminator that knows what a zebra is, like that. So this is cycle. It starts from horse, it continues, it goes to the loop, back to zebra until it's able to identify, convert the image into a real horse or whatever. The thing is cycle. You start from input of a horse, you pass through the discriminator, and then is it a horse? No. If it's a horse, then automatically it classifies as this is a zebra. no, then it passed through another discriminator that knows what a horse is. I hope this, I don't know if anybody want to explain this cyclic process more.
Excuse me, the G8 will be, both of them are the two distinct generators, while the DA and DB are the unique discriminators, just to clarify. So the input passes through the generator, and then it creates the images after it passes through some stages of learning. And after it generates the images, then the discriminator, who tends to find out if the image generated is true or it's fake or real, then takes over. Then after that, the same generated image will now pass through another generator in order to get the second image, which is the horse. And whatever is generated is also passed through DA, which is another discriminator, in order to get the real horse.
Okay, thank you very much, Tunde. Very important point. We have two generators and two discriminators. Thank you very much for that. I think we can move on. Okay, let's go and see how this works. So we are importing and initializing. When you run this, this we are just defining the RESTnet class. When you run this code for the first time, it will download. I've already run it, so but it will download a lot, a number of things that you have to wait for it. So we are defining a new RESTnet generator, loading pre-trained weights. The model had been pre-trained on horse zebra data set, whose training set contains two sets of 1,668 and 105 images of horses and zebras, respectively. So we've loaded our pre-trained model. Now we are going to input an image. No, we are going to take the image part, as we've done in the previous model. We are going to evaluate it. So we are importing our pre-processing. This we pre-process the image we want to use to transform. Then we are going to input an image, the image we want to transform. This we are defining the pre-process function, and this we are importing the image. We are going to use the function later on. Yeah, so here we are, this is our image, and this is the function for the pre-process. So we are outputting. So we are running this to see what happens. This is our model. So now we are outputting the image, and to see the image, we can see this is the original image we have, and it's a difficult image because it's not very clear. It's what do you call it? It's jumping. There is a person on top of it, whatever. And then after running this, this is what we have. It's able to identify the background and the person, and this looks like a zebra.
Shaurin kayan kalolin da ba a so sun rike ma wuya.
To fa why ke dinkin sallah? Okay, are we all together?
Yes.
Idris, want to say something on this? You use deep learning here the most.
Not yet.
Okay, nothing?
Yes.
So generally, this is this function that we run. You can try it. It takes this image that we have of a person on a horse, and it converts it into a horse using the cyclic gun. You can just download it from the GitHub and try it and see. There is a question here. Okay, not a question. And then finally, from me on this chapter, we have the Touch Hub. What is Touch Hub? The Pytorch 1.1 saw the introduction of Touch Hub, which is a mechanism through which authors can publish their model on GitHub. You have your model, you want to publish it on GitHub, so they have their own guideline that makes it better, with or without pre-trained weights, and expose it through an interface that Pytorch community understands. Generally, many people share their models on GitHub, but then many times you waste a lot of time trying to understand how to use that model. Specifically, if it is pre-trained, then you already want to use the pre-trained. How do you understand it and rest? So they have their own success, their own standard way that when everybody, let's say convention, when you follow that convention, so everybody in the Pytorch community can be able to understand your model. So this makes loading pre-trained model from third parties as easy as loading the Touch Vision model, meaning that the Touch Vision model we've just seen, that have the models we've seen, the rest and whatever, follows that syntax. So any model you want to run, if it follows the Pytorch standard of this Touch Hub, then you will use the same method to use it, which will make it a bit easy. Instead of for every model you have to go and read pre-trained model, you have to go and read their documentation, try to understand how to use it and the rest. So, and it's very easy to publish a model through the Touch Hub mechanism. You place a file named hub conf.py in the root of your GitHub repository. In our quest for interesting, now when you are searching the GitHub, you are looking for interesting pre-trained models that you want to use or models, then you can just include this parameter for it to include all models that have this file. So it will return only models that conform to this mechanism. So it's easy for you. So all the models that will return, you will be able to use them easily without needing to waste a lot of time trying to learn how it works. So we can try with the Touch Vision and see. Let's see. So this is the Touch Vision project on GitHub. And when we look down, we can see they have this. So all that is needed to do when you have your model is to include this file within it in this order. So this will